All right, this is the second hour of Physics 1B for October 20th, and we're now going to be talking about the heat capacities of gases. Now, in order to do this, we're going to have to think back to some things that we've learned in the past and combine them together. So what we want to do is we want to imagine, suppose that I have some collection of gas molecules. So I have in here some gas molecules, right? And within that gas, I have a bunch of different tiny little molecules that we now know are zipping off with extremely high velocities. Really high velocities. You know, we found that the RMS velocity, right, for hydrogen was something on the order of 2,000 meters per second. Just for reference, that's I think it's like 4,500 miles an hour or something like that. It's a lot. It's really fast. Much faster than any of us have ever traveled. It's faster than jets fly. Really faster than everything on the planet except for extremely tiny things. So we've got these gas molecules. They're zipping around inside of here, right? And what we want to think is, like, suppose that we were to add a burner to this gas and we heated it up, okay? So we dump some amount of heat into the gas, okay? So we take some amount of heat and we call that amount of heat dq, because, you know, that's always what we like to do is have little d's in front of everything. We dump a heat dq into the gas, and what we now know is that that's obviously going to increase the temperature of the gas, right? So this leads to a temperature increase. But we also know that a temperature increase is associated with an increase in kinetic energy as well, right? So what we can say is that by pumping this energy dq into the gas, the effect is that you're also going to be adding some amount of translational kinetic energy. So whatever the kinetic energy was before you added it, you're going to get an additional dk, translational, that's what this is, TR for translational. And all we could say is that any increase in translational motion of the gas must be due to this. So we should be able to equate the amount of heat that we put into the gas to the increase in kinetic energy of the gas, right? So to put this in words, what this says is that heat added must be equivalent to the increase in kinetic energy. That's where the D is, basically, because it's a change in kinetic energy. Okay? Does that seem reasonable? That we could just say all heat that we add to the gas, because it increases the temperature of the gas, that's really all that happens when you heat it up, right? Is the temperature goes up. Maybe the pressure changes too, but we know that the addition of heat increases the temperature of the gas. We also know that an increase in temperature is directly related to an increase in kinetic energy. So if the temperature goes up, the kinetic energy goes up. And if you wanted to know what had happened from an energy perspective, you basically say that the heat was converted into kinetic energy. That's another way of saying it, is that heat has now been converted into kinetic energy, right? Okay, so given that, we can now think about what each of these terms is going to be. Now, one way we can think about the amount of heat that we're adding into this system is by using our MCAT equation, or the MC delta T equation, right? But we have an equivalent version of this where we replace the mass with the number of moles, and we replace C with the specific heat at constant volume. So CV represents the specific heat. It's called the molar heat capacity is what it's called. The molar heat capacity, because it's in terms of moles. Molar heat capacity at constant volume. Okay. And then we would just have N times CV dt. Now, this is something that we derived when we were talking about specific heat, but we really haven't used it yet. You're going to see in the next chapter we're going to start using this a lot more, because we prefer to kind of talk about things in terms of moles instead of mass when we're talking about collections of gas molecules, right? So that's what we know dt is right there, dq. It's going to be N times molar heat capacity at constant volume times dV. Now, I say at constant volume because at some point in the future we're going to have a molar heat capacity at constant pressure called Cp. Anyway, we'll get there though. That's next chapter. So Cv. And we also know, and that's why I included all this stuff over here, that the translational kinetic energy of the gas is going to be given by the equation that we used earlier today, 3 halves nRT, but instead of having just a T, we'll put a dt in there because we're talking about a change in temperature, right? So we should be able to equate these two terms. And if we do that, so we put, we take this part right here, N times CV times dt. We equate that to 3 halves nRT dt. And then everything is going to cancel out except for CV and 3 halves of R. Okay? Look at that. This is specifically for monatomic gases. And what it says is that the molar heat capacity should be equal to 3 halves times the Rydberg, or times the gas constant. What's that equal to? So 3 halves multiplied by 8.31 joules per mole Kelvin is equal to about 12.5 or 12.47. And of course the units would also be joules per mole Kelvin. And if you look at this table right here, which lists the molar heat capacities of gases, you can see that that's actually a pretty good approximation for a monatomic gas, like something like helium or argon. Its molar heat capacity is about 12.47, exactly 3 halves times R. So what could this mean? Why does this exact 3 halves number keep showing up? We saw it show up with the 3 halves kT equation. It shows up in this equation. And now we're seeing it show up again as a way to calculate the molar heat capacity. So the 3 halves has to mean something, right? So let's talk about where it comes from. Okay, so we're gonna read what this says right here because I wanted to, I think it's important and I wanted to include it here. So we're gonna read this. Yeah. Go ahead.
How can you tell whether a gas is monotonic?
You have to kind of be told.
Gotcha.
All right. So stuff like hydrogen, nitrogen, oxygen, carbon monoxide, those are diatomic. So diatomic means exactly 2, right? So HHNNOOCO, right? And then polyatomic is going to be these ones right here. And you'll notice on this graph that as soon as you get to the diatomic gases, you start getting these numbers right here, right? And you might wonder, okay, these are all relatively close together. They're all about 20.8, 20.4. It's basically in the same range right here. Maybe there's a way that we could say that the CV is also equal to something here, and we can. It's going to be 5 halves R for these. And it's going to be 7 halves R for these, although these are less accurate. So where's that 5 halves coming from? All right, so this requires us to talk about what's called the equipartition of energy. This is something we're not going to prove in this class, but if you go on and you take more advanced classes in thermodynamics, it's something you can actually prove. And of course, you can go read about it on the internet if you want to, and you can learn how to prove it. But it says that the principle of equipartition of energy states that each velocity component, either linear or angular, has on average an associated kinetic energy per molecule of 1/2 kT. Now I want you to remember this equation that we had from earlier, which was that the average kinetic energy per molecule, right, which we wrote like this, was equal to 3/2 kT, right? We had that equation, right? And what it's telling us is the reason why there's a 3 there is because for an individual gas molecule, let's say over here we have an individual gas molecule, and it's moving through space, we can describe its x velocity, its y velocity, and its z velocity. That is to say, it's free to move like this, it's free to move like this, and it's also free to move in and out. Those 3, what we call degrees of freedom, each contribute 1/2 kT to the associated kinetic energy per molecule, or 1/2 blah, 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 blah. The number of velocity components needed to describe the motion of a molecule completely is called the number of degrees of freedom. For a monatomic gas, there are 3 degrees of freedom for the 3 velocity components, Vx, Vy, and Vz. And that's all that you can really have, right? And that gives a total average kinetic energy per molecule of 3/2 kg, something that we already derived earlier. In fact, if you go back to the derivation, the reason why the 3 showed up in the equation at all was because we said that we could take the average velocity and relate it to the x velocity by multiplying by 3. I don't know if you remember the step that we did where we said Vx Vx squared average plus
The
Vy. What's up?
The assumption we made.
Yeah, we made an assumption that if we're talking about average velocities, that we can assume that there's nothing special about Vx average, Vy average, and Vz average. They should all be the same. They should basically all be equal to each other. And we said that's going to be equal to V squared average. But then we said, oh, but well, this is probably the same as this is probably the same as this, because if you were to rotate your coordinate system, you wouldn't expect any changes in the average motions. So as a result, we basically said if I take Vx squared average and I multiply by 3, this is equal to V squared average. And that's exactly why this 3 showed up right here. That's where the 3 came from. And why did that 3 show up? Because there's 3 dimensions to our space, right? 3 spatial dimensions. That's what we have, right? We have 3 spatial dimensions and 1 time dimension. The 3 spatial dimensions mean you get 3 halves kVt. If we lived in a 4-dimensional universe, it would be 4 halves kT. But we don't. We live in a 3-dimensional universe, as far as we know. So we have 3 halves kT. So the question then becomes, what about things that have angular velocity, right? Because it's not just the case that a molecule moving in space can move in space, but it could also, if for example it was a diatomic molecule, imagine that we have a diatomic molecule and it's shaped like a barbell, kind of like this right here, right? You've got your hydrogen here, you've got your hydrogen here. Well, this molecule can also rotate, right? And it could rotate not only about that axis, but it could also, that's awful, it could also rotate about an axis up and down. So I include this picture because I don't want to try to draw this, but we can imagine that for rotational motion, the molecule can rotate about its center of mass, and it has 2 independent axes of rotation, okay? So we can imagine that it can rotate about the y-axis, we can imagine that it can rotate about the z-axis, we can also imagine that it can rotate about the x-axis. We're not going to include this one, though. And the reason why is because the molecules themselves will be spinning, and supposedly in the collisions, this one actually can't be altered. And I believe it's related to something that's called intrinsic spin, if you all know what that is. Do you all know what intrinsic spin is? Has anyone heard that before? What about saying that an electron has a spin of plus or minus 1/2? Have you all heard of that before? Saying an electron has a spin of plus or minus 1/2. None of you have heard of that before? Need more people in this class. Someone must have taken chemistry. Is anyone here taking chemistry? No? Yeah? No one? Yes. You don't remember that? Saying that you can have an electron? It's okay. So the people just weren't speaking up. I knew someone had to heard about it. When you look at electrons, they basically spin. Do they really spin? I don't know. But they have this property that has angular momentum, and we call it their spin. And it happens to be the case that the size of the spin is basically equal to plus or minus h bar divided by 2. And it's a type of intrinsic spin. This intrinsic spin is associated with producing magnetic moments and magnets and stuff like that, but the symbol h bar, if you don't know what it is, h bar is equal to h divided by 2 pi. H is the Planck's constant. You should all really take chemistry, by the way. I don't know if your thing tells you have to take chemistry, but you should take chemistry. It's really fascinating, and you know, if you want to be a really good anything, engineer, biologist, chemist, physicist, whatever you're going into, you need to know about the other sciences, because a lot of the really interesting new discoveries that occur are kind of at the interface between the sciences, right? Where physics and chemistry meet, or where chemistry and biology meet, or physics and biology meet. It's being able to understand both ideas, how a chemist would approach something or how a physicist would approach something, that helps you to kind of discover new things. Anyway, I think that's what's going on here. We say that for a molecule that there's going to be only 2 rotational motions that are going to contribute to this, okay? And so we can say basically that if you have a diatomic molecule, okay, that's going to have a molar heat capacity of about 5/2 R. And for molecule, we can also have molecules that vibrate too, like a spring, and that's an additional degree of freedom. But polyatomic molecules, you get something closer to 7/2 R. Man, that's pretty much it. the biggest takeaway from this is that each degree of freedom, okay, contributes 1/2 kT. So I think another thing that we can say, although your book doesn't explicitly say this, unless I'm crazy. No, they don't talk about this. Another thing we could say is I think that if we wanted to know the kinetic energy per molecule for a diatomic molecule, I think you would have 5/2 kT. I mean, that's what I take away from reading this. And that's what I remember from doing in my classes that I took. So, something to think about. That for a diatomic molecule, now the kinetic energy per molecule is going to be 5/2 kT because it's going to have these additional degrees of freedom. We're going to hear more about degrees of freedom, but they basically just represent the motion that a particle can undertake, right? So it has 3 degrees of freedom for space, and now it's going to have 2 degrees of freedom for rotation. Y'all have any questions? Diatomic, right? This is all diatomic right here.
Can you explain one more time how you related the 5/2 kBT equals the 1/2 mv squared average?
So if it's all from this right here. It says that each velocity component, whether it's linear or angular, has on average an associated kinetic energy per molecule of 1/2 kT, right? So if you have a monatomic molecule that has no rotation and it's just moving, it has 1, 2, 3 degrees of freedom. Does that make sense?
Yeah.
But if we allow it to rotate as well, so this is not a monatomic molecule, this would be a diatomic molecule, right? The monatomic molecule would just be a ball, a point-like particle moving through space, and we don't worry about any of its rotations. The diatomic molecule, on the other hand, it can spin like this, right? It can be vibrating like this, but can also, I don't know how well you can see this, but it can also rotate like this, right? It could rotate around the y-axis, or it could rotate around the z-axis, basically. It can rotate like this, right? Or it could rotate kind of into the page and out of it. Like that. And we consider those to be 2 independent degrees of freedom, which contribute an extra 1/2 kT per each one. So how many degrees of freedom does the diatomic molecule have? It has 1, 2, 3, 4, 5. Those are kind of like the ways in which it can freely rotate in space, right?
Yeah.
Does that make sense? You can talk about, by the way, degrees of freedom can be expanded to anything. We can talk about degrees of freedom, like for my body, right? I could say that as I move through space, right, I have 1 degree of freedom that I can walk this way. I have another degree of freedom that I can walk left and right, right? I have another degree of freedom that I can jump up and down, right? That's 3. But I can also do things like spin around. And I can curl up into a ball and roll, right? So maybe I have like 5 degrees of freedom. It's like, what are the 5 possible ways that I can move? And you think about the same thing for a molecule. For the molecule, we say there's exactly 5. And so, on average, the molecule is going to have an energy of 5/2 kT. That means that the kinetic energy for a diatomic gas is going to be higher, right? That's what this means, basically. And that's partially because the gas itself can hold that energy. That higher temperature can be held in 5 different ways. In X motion, Y motion, Z motion, we call it theta motion and phi motion, right? All of those different ways are how it can hold its energy. Does that make sense?
Thank you. Yeah, it does.
Anyone have any questions? So we're done. We finished a little earlier tonight than I did with my other class. I think with my other class I spent about 30 minutes talking about spin, and I'm gonna save you all the trouble of not having to listen to me talk about that. But I will say that if you've never heard of this before, intrinsic spin, you should go read about it. It's a very fascinating topic because it turns out that when you're constructing the periodic table, the construction of the periodic table is entirely determined by this thing that we call electron spin and how many electrons you can put into what's called an orbital. It turns out that with hydrogen and helium, you completely fill up the first orbital because one of the rules is you can't put 2 electrons in the same orbital that have the same spin. So if you have an orbital and I can put a total of 2 electrons in there, and I tell you that electrons can only have a spin of plus or minus 1/2. Something called the Pauli exclusion rule says I can't put two electrons into the same quantum state that have the same spin. That means that in a helium atom, how many electrons are there in a helium atom? 2, right? So the first orbital has room for 2 electrons. One of them is spin up and one of them is spin down. Okay? And as you go to the next level here, you get a third electron. That third electron cannot fit into the first orbital, so it has to go into the second orbital. That second orbital, if I remember correctly, can hold a total of 8 electrons, I think. Is this stuff coming back to you now? Yeah. The second orbital can hold a total of 8 electrons. Is that right? And so on and so forth. And the order of the periodic table is entirely dependent on one rule, that if you have 2 fermions, electrons are fermions because they have spin 1/2, you can't put 2 fermions into the same quantum state unless they have different quantum numbers. Quantum numbers for the electron are things like charge. Electrons already have the same charge, so the only thing to distinguish between one electron and another electron is its spin. If you go deeper into the details of this idea of spin, it gets really weird because, I mean, we think of electrons as point-like particles, right? We really believe that electrons have virtually no size to them, right? Now, if you have something that has size, like this cup right here, it's not hard to imagine how it could rotate, right? But what would a point rotating look like? Think about that. What would a point rotating look like? What is a point? How would you define a point? Anyone have a good mathematical definition of what a point is? No volume? Sure. Yeah, an object with no volume, right? X, Y, Z, that could represent a coordinate, right? But yeah, we kind of think of points as having no volume. In fact, the first definition of a point that I think you can find in literature is coming from Euclid. And Euclid defined a point is that which has no part. That's what he says. A point is that which has no part. I think that's a really nice definition. A point is that which has no part. It's made up of nothing, right? It's made up of nothing. So if it has no volume, if it has no size, then how can it rotate? You know? Like, I know that this is rotating because I can see the pieces of it move, right? Because it's large. But a single point, how could it possibly rotate? So this is a fundamental problem within physics, which is like, we know electrons have this thing that we call spin. It has units of angular momentum, and we say that they're spinning. And they even exhibit properties of things that spin. But it's really hard for us to imagine what's spinning. You know what I mean? What is the thing that's spinning here? Anyway, so some things to think about. We're going to stop early tonight, actually, because we covered all the stuff that I wanted to cover. And next week we'll get into the next chapter, which is chapter 19 on the second law of thermodynamics, which is quite interesting. So are there any questions about anything before we stop? No questions? Okay. So let's stop then. By the way, this is kind of what the electron orbitals look like. So the lowest state, they kind of move in circles. But then when you get to these higher states right here, these represent the kind of path that the electrons move along here. And it's these beautiful, like, kind of clover patterns. They're actually three-dimensional, so this doesn't really do justice to it, but really quite beautiful. Triatomic model says 7 degrees of freedom. Yep, that's right. I think that's correct. All right. Let's stop.